Welcome to our presentation for the MSIM 605 term project. Our project focuses on the AEGIS weapon system Detect to Engage sequence. This presentation will cover the following items. First, we will introduce our team. Then we will give a brief overview of the project, followed by our project objectives. We will present background information on the real-world system being modeled and discuss the conceptual model we created. We will then present the programmed model, data analysis, and provide a discussion on the assumptions and simplifications we used, in addition to discussing future projects that can build on this model. We will conclude with some lessons learned from this project. Our team is made up of 3 diverse individuals. Amanda White is a lieutenant in the Navy with a background in anti-submarine and anti-air warfare. Mark Brooks is a mechanical engineer who works for the Navy on project design. Mark Ingraham is a graduate student with a background in biology, psychology, logistics, and computer science. The goal of this project is to model the real-world AEGIS weapon system during its Detect to Engage sequence using a Petri net. The Petri net execution will provide a visualization of how the sequence evolves while demonstrating component interactions. The objectives of this project are listed on the slide. The primary objective is to explore in detail a real-world system while gaining further understanding and knowledge of the Petri net modeling paradigm. Additionally, knowledge of the Detect to Engage sequence is required of most surface-qualified junior officers in the Navy. With some refinement, our project can be used as a training tool to demonstrate system and component interactions to aspiring naval officers. The AEGIS weapon system, or AWS, is the primary component of the AEGIS combat system located on guided missile cruisers and destroyers in the United States Navy. It provides automatic self-defense capabilities against hostile missiles. The Detect to Engage sequence, one process of AWS, executes when a contact is detected on radar, identified as hostile, tracked, and engaged with ship self-defense weapons. The AEGIS weapon system is composed of 9 subsystems listed on the slide. We will give a brief overview of the first 7, which are used in the Detect to Engage sequence. The AN SPY-1 radar is the air search radar used by the system to detect and track airborne contacts. The Standard Missile, SM-2, is the default self-defense weapon on ships. The AEGIS Display System, or ADS, gives the user a graphical depiction of the track while providing contact data such as altitude, speed, range, etc. Command and Decision, CND, is the user interface that allows operators to interact with the system. WCS, the weapon control system, coordinates the engagement by talking to the various other system components. The Fire Control System, or FCS, provides terminal homing guidance to the SM-2, completing the engagement. VLS, the vertical launch system, is made up of missile tubes that house and launch the SM-2. The 2 systems not involved in the Detect to Engage sequence are ORTS and ACS, which provide maintenance and training capabilities. This slide depicts our conceptual model. We use this model to generate our Petri net. The conceptual model steps through the component interactions in a basic, high-level fashion. At system start, a radar contact is detected and identified as a friend or foe. If the target is a friend, for the purposes of this simulation, it is dropped, since we are only interested in targets that we can engage. The next step is to identify it hostile. If the target is not hostile, it will be tracked and displayed. If it is hostile, the track is passed to WCS, which initializes the vertical launch system and fire control systems. FIS, the fire inhibit switch, one of the safeties in AWS, has 2 states, green or red. If FIS is green, you are able to launch. The next safety is launch enable, which must be enabled in order for the missiles to launch. VLS selects a missile type of the 4 shown on the slide. Once a missile is selected and launched, it is uplinked to the SPY-1 radar. FCS provides terminal homing guidance, and the hostile target is engaged with the SM-2. The system then determines if the original track is still valid, namely, has it been killed or not. If the track is valid, then the sequence repeats. If the track is not valid, it has been destroyed and the sequence ends.
This slide shows our program model, which was created in CPN Tools. In the bottom left-hand corner is a transition called initialize, which has 50 tokens associated with it. When radar hits its 90% chance, the program is started and the simulation runs. After hitting that 90% chance, initialize sends tokens to 3 places: radar, IFF, and FIS. After receiving those tokens, transition 1 is able to fire, sending a token to number of tracks, which is a counter of how many tracks the radar made, and also to hostile, which is a 60% chance that the object is hostile. Once receiving that token, transition 3 fires, displaying and tracking the unknown hostile object. And then transition 2 fires, tracking how many times the object is hostile, and also sending a token to WCS. Once WCS receives the token, transition 4 is then able to fire, sending tokens to VLS, LE, and FCS. Before VLS can move any farther, the random generator has to send tokens to VLS, which can send anywhere from 0 to 3 tokens. Once VLS receives its amount of tokens, it then chooses which missile block is going to fire. After choosing that, and the necessary transitions are fired, radar uplink then receives a token, as well as the counters that are associated with each missile block. Once radar uplink receives its token, transition 13 fires, and then engage receives the tokens. Now this is where the simulation either says the object is destroyed, thus ending that part of the simulation, or transition 14 is fired, restarting the whole engagement process on the object. Next is our analysis. We ran the model 10 times, recording how many steps it took to complete the simulation, how many times the radar tracked an object, how many times that object was hostile, how many times each missile block fired, how many times it was necessary to re-engage the objects, and how many it destroyed total. If you notice, it took an average of 338 steps to fire in order to complete the simulation. The radar tracked roughly 40 objects out of the 50 possible tokens, and each missile block was used roughly the same amount of times, and it averaged about 14 re-engages and also destroyed an average of 20 hostiles. Further analysis showed that several missiles did not reach their targets. On average, 14 tracks were re-engaged per run. Also, missile supply was unlimited. The launching ship did not run out of ammunition. All of the 20 hostile contacts per run were shot down. No hostile tracks remained at the end of any simulation. There were several assumptions made. The target of interest must be identified as hostile for the simulation to continue. Also, the radar detection probability was around 90%, and all firing safeties were turned off. In order to simplify our model, the initialization had 50 marks and the simulation ran until deadlock. The model is fully automated. Each transition fires based on the probabilities that govern those transitions. Radar and missile uplink downlink was not modeled for simplification reasons, and the simulation generates how many hostiles to engage based on the probabilities. Why Petri nets? Petri nets are preferred over a discrete event simulation because Petri nets allow modeling of conflict among resources and multiple decisions that must be made in scheduling. DES and FSA models also require excessive computational time for the required task, and Petri nets do not require separate entity states and characteristics to be simulated and stored in memory. If the model was intended as a thorough, continuous simulation, physical simulations would have to be developed for inbound aircraft. Also, weather and sea state conditions would be modeled, and standard missile aerodynamics and warhead capabilities would have to be modeled also. Characteristics which could be simulated through detailed models are simplified in the Petri net approach to reduce computational time and model complexity. What kind of future projects could come from this simulation? AWS is a complex system with multiple functions. Other aspects of the AWS system can be modeled and also integrated with the detect to engage sequence using a multi-model. Multiple target engagements can be integrated using a queuing system. Radar transition to track processes can be modeled using finite state automata. In conclusion, the model and simulation was an overall success. Petri nets, we found out, are an effective way to simulate this system. They allow for a relatively simple and accurate method of simulating complex phenomena. And this concludes our presentation. Thank you.